In connection to the presentation of exponential function for complex numbers, let's try to prove these two identities, one for this video and one for the next one. These two videos are actually related to the loss of exponents, basically on the addition, the multiplication where we add exponents, and for the quotient rule where we subtract exponents. So for this time, we're going to show that the product of e to the power of z sub 1 and e to the power of z sub 2 is just equal to e to the power of z sub 1 plus z sub 2. As mentioned, similar to the multiplication law, we're going to multiply exponentiation with the same base, we add exponents. But here, we're going to show that this is true for e to the power of, let's say, z is equal to this notation, e to the power of x plus iy. Okay? Or, it could be expressed in this manner, e to the power of x times cosine y plus I sine y. These are the three representations for an exponential equation in this manner. So, for this video, allow me to use this one here, okay? Because this, with the use of the second one, we are still going to use the concept of what we call this one, the basic the loss of exponent for real numbers. But since I is present here, let me use the second notation to illustrate our solution here. So how do we show the result for this specific item? One thing would be done here is to let, okay, so we're going to let, this is the proof here, okay, e to the power of z sub 1 be equal to e to the power of x sub 1 plus I y sub 1 or y sub 1i, which is also equivalent to e in this notation, e to the power of x sub 1 times cosine of y sub 1 plus I sine of y sub 1. Okay? That's the first notation we are going to use here. Now, second, of course, also let the second as e to the power of x sub 2 plus I y sub 2, or again, e to the power of x sub 2 times cosine y sub 2 plus I sine y sub 2. So here comes the first part of this proof. Then we have here e to the power of z sub 1 times e to the power of z sub 2. Using these notations here, this one and this one here, is actually equal to e to the power of x sub 1 times cosine y sub 1 plus I sine y sub 1. Okay? That's for the first. Times e to the power of x sub 2 times cosine y sub 2 plus I sine y sub 2. Okay? So we're going to show that this will actually result to, again, the sum, okay, of the exponents. So, let's manipulate this. This is actually equivalent to, when we multiply this and that, you have e to the power of x sub 1 plus x sub 2. And this time, x sub 1 and x sub 2, as we know, as real parts of our complex numbers. Hence, we can simply use here the loss of exponents for the x's. Okay, that's why I use the second notation instead of this one here, because it has, instead of this one here, because it has an exponent which are actually imaginary in nature. So let me use that and only apply the loss of exponents for the real real parts. So for the next one, we have here cosine of y sub 1 plus I sine y sub 1 times cosine of y sub 2 plus I sine of y sub 2. So this is really okay. The first term is really okay, because if we're going to look at this one here, later on we're going to connect it to that. The next part here is to multiply the two binomial expressions here. So we're going to use the FOIL method. So this one and that will become cosine y sub 1 cosine y sub 2, right? Inner terms plus I sine y sub 1 cosine y sub 2. Outer terms plus, I'm going to write it in this manner because I guess the spaces are not enough, I sine y sub 2 cosine y sub 1. Or you can rearrange this one here so that all y sub 1s will be the first in every term. So cosine y sub 1 sine y sub 2. This one and that. And finally, for the last terms, you will have here plus I squared sine y sub 1 sine y sub 2. Okay? So this is still equal to e to the power of x sub 1 plus x sub 2. Right? So this time, this is actually product of take note of this. I'm going to make this my second term. Okay, the first term will still be cosine y sub 1 cosine y sub 2. Allow me to make this as my second term, but of course taking into consideration that when we have here the square of I, that's negative 1. So that would mean I have here negative 1 of sine y sub 1 and sine y sub 2. And then I'm going to combine these two by factoring out I. So you have here plus I times, you have your sine y sub 1 cosine y sub 2 plus cosine y sub 1 and sine y sub 2. Okay? So these are all the result here. I'm doing that because I would like to pair this one here. That's actually an example of a difference formula, or specifically the sum formula for cosine. If it's minus, it can be written in this manner. So you will have here e to the power of x sub 1 plus x sub 2. This one here is the cosine sum. The signs are opposite. So you will have here times cosine of y sub 1 plus y sub 2. Okay? So if minus, it's plus. That's for the sum and difference formulas for cosine. As for the second one, plus I. And this we have here sine of the first angle, cosine of the second angle, plus cosine of the first angle and sine of the second angle. It's actually the sum formula for sine. So you have the sine of the sum of y sub 1 and y sub 2. Okay. Now from this point here, okay, take note that we have here the sum of the first, the real parts. We have the sum of the coefficients of the, what do you call this one? The coefficients of our imaginary part. Now, when we're talking about this one, this is actually basically similar to this form already. This one here. We have here x, that's the real part, and this would be the coefficient of the imaginary part. Similarly here, x is the real part, and this would actually be the coefficients of the imaginary part. So similar here, this would be our real part, meaning we can rewrite this in this manner: e to the power of x sub 1 plus x sub 2, your real part, plus, look into this one here, the real part plus your I times your the coefficient of imaginary part. You have your I times y sub 1 plus y sub 2. This represents the angle, and this represents that one here. So vice versa, this would represent the angle here. The angle is representing your coefficient in the imaginary part, and this becomes your real part. So what is this equivalent to? Okay, we can now actually look into this perspective that x sub 1 and x sub 2 together with y sub 1 and y sub 2 are actually the sums of the coefficients of your z sub 1 and z sub 2. Okay, this will be the sum of the real part, and that's the sum of the imaginary part. Just like if you have here z sub 1 be equal to x sub 1 plus I y sub 1, and your z sub 2 is x sub 2 plus I y sub 2. If we're going to add them, coming up with the sum, okay, z sub 1 plus z sub 2 is equivalent to the sum of the components here plus the sum of this, and when we factor out y, we're just going to add y sub 1 and y sub 2. So generally, the entire form for this is just equal to e to the power of z sub 1 plus z sub 2. And this shows the multiplication law for the exponents when the exponents are actually complex numbers. It shows that when we multiply two exponential forms of complex numbers with the same base, of course, we're simply going to add the exponents copying the same base. This is the proof for this one, and we will have a separate video for the other law as well. Thank you very much for watching.